Okay, our final lesson, lesson 10, is on independent and dependent events and conditional probability. So the first kind of event we're going to look at are these independent events. Independent events, occurrence of one has no effect on the occurrence of the other. So in a way they are unrelated. So when we find their probability, the probability of A and B, we can just take each separate probability and multiply them together because they are unrelated. So here are a few examples of that. You draw 3 cards from a standard deck with replacement. What is the probability that you draw an ace, then a face card, then a red card? So we want the probability of pulling an ace, the probability of pulling a face card, and then the probability of pulling a red card. These are independent events because we are replacing the card each time, so we can find each probability and multiply. Ace. There are 4 aces in a deck of 52 cards. Face cards. There are 12 face cards in a deck of 52. And red cards, that would be 26 in a deck of 52. And then you could reduce and multiply that to get your answer. Here's a little bit tougher one. It says you roll a die 8 times. Find the probability, here's the tough words, that at least one roll is a 6. Well, at least one roll is a 6, and if you're rolling it 8 times, that would be 1 roll is a 6, or 2 rolls is a 6, or 3, or 4, or 5, or 6, etc. So that's going to be a lot of different cases. So instead of considering all of those cases, we're going to use the idea of a complement, and we're going to take 1 minus the probability that there are no 6s. Okay? So instead of considering the probability that at least one roll is a 6, I'm going to take 1, which represents like 100% if you want to think of it that way, and just subtract the probability that none of them are. All right, now let's think. There are 8 times that we're rolling the die. So if you want to think of it as blanks, we had 8 blanks. We do not want to roll a 6. Well, there are 6 sides on the die. One of them is a 6. So if I don't want a 6, I'm okay with any of the other 5 on that die. So in each case, my probability would be 5 out of 6 that I do not roll a 6. Okay. So 1 minus that, I could write that as 1 minus 5/6 to the 8th power. That actually comes out to be about 0.767, or close to 77%. All right, let's think of it in terms of free throws for you basketball people. Steve Nash retired from the Los Angeles Lakers. He had the best overall free throw shooting percentage in the history of the NBA at 90.4%. That's like giving you the probability. So the probability he would make a free throw is 90.4%. He attempted 10 free throws. So just like here we were rolling the die 8 times, we're attempting 10. What is the probability that he would miss at least 1? All right, so missing at least 1. Again, those words at least are a problem because we'd have to consider missing 1, missing 2, missing 3, missing 4, all the way up to missing 10. That's way too many cases. So again, we'll use this idea of a complement. The probability that he would miss at least 1 would be the same as 1 minus the probability that he would miss none. Well, that's 1 minus. Now again, remember we're talking about 10 free throws he's shooting, right? And what's the probability that he would not miss? Well, the probability that he makes a free throw is 90.4, so that's the probability that he would not miss. If I write that as a decimal, let's call that 0.904. So 0.904 in each one of those. So that would be 1 minus 0.904 to the 10th. That's again the probability that he would miss none. Well, they're telling you the probability that he makes a free throw is 90.4. So I can put that in as a decimal in each one of those 10 blanks because I'm looking for the probability that he misses none. That comes out to be approximately 0.6 355, which would be about 63.55% chance that he would miss at least one, even though he's such a great free throw shooter. So if we take the same case for those of you who remember Shaquille O'Neal, who was not a very good free throw shooter, teams would foul him on purpose. In 2006-2007, his free throw shooting percentage was only 42.2%. If he attempted 10 free throws, let's calculate the probability that he would miss at least one. So same kind of calculation, but you can see his free throw shooting percentage is a lot worse. So once again, we would do, to get missing at least one, we could do 1 minus the probability that he would miss none, which would be 1 minus, and then we'd have these 10 blanks. And his free throw shooting percentage was 42.2%, so the probability that he would not miss would be 0.422 in each one of those blanks. So 1 minus 0.422, and we were talking about making 10 free throws. If you calculate that, you get approximately 0.9998, so there would be a 99.98% chance that Shaq would miss at least one free throw if he shot 10. All right, let's switch gears here. At the bottom of the page here, we're going to talk about dependent events. This is a little bit tougher because this is the occurrence of one affects the outcome of the other. So they are interrelated in some way. So here's kind of a real basic example. It says, imagine a couple with 2 children, each of whom is equally likely to be a boy or a girl. So if we wanted to list outcomes, first could be a boy, second could be a boy. First could be a boy, second could be a girl. First could be a girl, second could be a boy. First could be a girl, second could be a girl. It seems like that should be my bottom number 4. But now it says, now suppose you are given the information that one child is a boy. So notice now, knowing that one child is a boy means I have to rule out that case, so I really only have 3 as my bottom number. And then what is the probability that the other child is a boy? Well, out of those 3 possibilities, what's the probability that one is a boy and the other is a boy? That's just that first case, so that's just 1 out of 3. Okay, let's look at it in terms of cards. This may make it clearer for you. You randomly select 2 cards from a standard 52 card deck. What is the probability that the first card is the ace of clubs and the second card is a black card if, now notice the difference here, first we're going to replace and then we're going to not replace. So if we're replacing the first card before selecting the second, this actually would be independent events. One pick would not affect the other pick because you're putting that card back in the deck. So we want the probability of an ace of clubs, whoops, and the probability that the second card is a black card. We could multiply those probabilities together. Probability that you pick an ace of clubs. There's only one ace of clubs in the deck. But now I take that ace of clubs and I put it back in the deck, so there are still 52 cards. How many of them are black? Well, the whole deck is there, so half of those cards are black. You could multiply that and get your answer. Now, if we do not replace, let's look at how this changes, right? I still have the probability of getting an ace of clubs and the probability of pulling a black card. All right, so the first one doesn't change. I've got a full deck of cards, I've got 52 cards, and I want to pull the ace of clubs, of which there is just one. But now remember, I'm not replacing that card. So there are no longer 52 cards in the deck because I've pulled the ace of clubs. So I've pulled that one card out, so now there are only 51 cards left in the deck. And of those 51 cards, I need to know how many are black. Well, think, the card that you pulled out was the ace of clubs. That is a black card. So although there are normally 26 black cards, this card that we pulled and left out of the deck is black, which means that I'm only going to have 25. That is a nice example of dependent events where this second pick was based on this first event because the card was not replaced. So I was one card short in the deck, and I was actually one black card short in the deck, so it affected the top number as well. All right, let's turn the page. Let's take another look here with cards. You randomly select 5 cards without replacement. What is the probability of selecting the following? Just set up the work. So similar to what we just did. My first pick is not a problem. I have 52 cards in the deck, and I need to pick the Ace of Hearts. There is only one Ace of Hearts in the deck, so it's 1 out of 52. But now remember, I'm not replacing that Ace of Hearts, so that is now gone. So now when I go to pull for the King of Diamonds, there are only 51 cards in the deck. How many King of Diamonds are in the deck? Well, I pulled out the Ace of Hearts, so the King of Diamonds is still there, and there's only one of those, so I put a 1 on top. But now out of the deck came the Ace of Hearts and the King of Diamonds. That's 2 cards. So when I go to pull for a red card, I'm down to 50 cards left to choose from. And I need to know how many are red. Well, I know normally there are 26 red cards in a deck, except that I pulled out the King of Diamonds and the Ace of Hearts. Both of those are red cards. So of this 26, 2 of them are already out of the deck, which means I only now have 24. So it does impact the top number this time as well. All right, so some red card came out of the deck. The Ace of Hearts came out, the King of Diamonds, and now another red card. That's 3 cards out of the deck, so I'm down to 49 cards to choose from. I now want to pull a black ace. Well, I've only pulled red cards out up to this point, so all the black aces are still in there. There's an Ace of Clubs and an Ace of Spades. That's 2 black aces that are in the deck. All right, pull one of those out. Now I need to pull a black face card. Well, I've pulled 4 cards out of the deck already. So if I take 52 and I remove 4 cards, that means there are 48 cards left to choose from. How many black face cards are in the deck? Well, if you look back, you will see that we have not pulled any black face cards. Face cards, again, are Jack, Queen, and King, but I have a Jack, Queen, and King of Clubs, and I have a Jack, Queen, and King of Spades that would all satisfy the black cards. All of those are still in the deck, so that would be a 6. All right, let's talk about an urn. An urn contains 5 blue and 7 red marbles. 2 marbles are chosen at random, one after the other. Here's what's key here, without replacement. So that means that first pick could impact the second pick. What is the probability that both marbles are blue? So I want the probability of a blue times the probability of a blue. All right, so let's think. There are 5 blue and 7 red. That's a total of 12 marbles. So I have 12 marbles in the urn to pick from the first time. I'm picking a blue one. There are 5 blues, so I put 5 on top. That's the same that we've done. But now I did not replace that marble, so I have pulled a blue one out. So now there are only 11 marbles. I'm pulling another blue. Well, this first one that I pulled out was a blue marble. So even though I had 5 to start, 1 came out on the first pick. So now I only have 4. And that's how I would calculate part A. Part B says, what is the probability that the second marble is blue, but the first marble is not? Well, the only other color besides blue is red. So if I want the second marble to be blue, and the first marble is not must mean that it's red. So I want the probability of red first, right? And then times probability of blue. So I have 12 marbles in the urn. 7 of them are red. So 7 of 12 is what I have to pick from to get a red. Times. I've taken that red marble now and I've removed it from the urn. So there are no longer 12 marbles left. There are 11. But this time I'm picking a blue. I haven't touched any blues because the first pick had to do with red. So all of the blue marbles should still be in the urn, which means there are 5 of them. And that's how you would calculate part B. Part C, what is the probability that the second marble is blue? I hope you realize here we have a couple of cases because it doesn't tell us anything about the first marble. So we have 2 separate cases. We have the case where the first one could be red and the second one could be blue. Or right? The second one just has to be blue, so the first one could be blue and the second one could be blue. So those are the two options I have. I believe I've already calculated both of these, right? Probability of red, then blue. That was 7 over 12 times 5 over 11. Right? We know or translates to plus, because these are separate cases. Probability of blue and blue, that's what we did up here. 5 out of 12 times 4 out of 11, that would get you your answer. Part D, what is the probability that at least one of the marbles is blue? All right, at least one. So we could do probability of red, probability of blue, or we could do probability of blue, probability of red. At least one also means both of them could be blue. So that's actually 3 cases, but hopefully you're thinking about that complement, because I think that's the easier way to go. Instead of calculating all 3 cases and adding them up, couldn't we do 1 minus the probability that none are blue? If none are blue, doesn't that mean that that would be a red and a red? So let's calculate that probability. 1 minus, what's the probability that I'd pull 2 reds? Well, there are 12 marbles, 7 are red. But then I've pulled one of the red marbles out, so now there's only 11. There are no longer 7 red marbles because I pulled one out right here, so there are only 6. And so that might be a quicker way to calculate it than doing all 3 cases. All right, we're going to look at a little different style of problem down here, and on the next page, we're going to use trees to help us make these probabilities. It says, suppose that one urn contains 3 blue and 4 red marbles. So that's sort of our first urn here, 3 blue, 4 red, and then we have a second urn that has 5 blue and 3 red. A marble is selected by choosing one urn. So first thing we have to do is choose an urn. So let's say we have urn 1 and urn 2. Right? If there are 2 urns and they're equally likely, it would be 1 out of a 2 chance that I pick urn 1 and 1 out of 2 chances that I pick urn 2. All right, let's go back to urn 1. Urn 1, right, contained 3 blue and 4 red marbles. So in here, I could get blue or I could get red. There are a total of 7 marbles, so the probability that I would pick a blue one would be 3 out of those 7. And of the 7 marbles, 4 are red, so the probability that I would pick a red out of that urn would be 4/7. All right, I'm going to do the same for urn 2. I'm making this tree diagram. Within urn 2, I have blue marbles and red marbles. I have 5 blue and 3 red. That's a total of 8 marbles I'm picking from. So the probability that I would pick a blue would be 5 out of those 8, and the probability that I'd pick a red out of the second urn would be 3. All right, so you see I have 2 choices to make. First I have to pick an urn, and then once I pick an urn, I would be either picking a blue or a red from that urn. So the question says, if the chosen marble is blue, that's key because this is telling us what we're choosing from. So my bottom number is if blue, right? What is the probability that it came from urn 1? So on top, we'd have to have a blue from 1. So the probability that I'm getting a blue marble from urn 1 out of all the possible ways to pick blue marbles. All right, let's think about what that is. All right, let's start on the bottom. How many different ways can I get a blue marble? I could pick urn 1 and then pick a blue marble, or I could get urn 2 and then pick a blue marble. All right, so these are part of the same choice, so I multiply those probabilities, so that would be 1/2 times 3/7, or, so since it's an or, that's my second case, I would do 1/2 times 5/8. Those are my 2 separate cases, urn 1 picking blue or urn 2 picking blue. All right, that's assuming it said if we chose a marble that is blue. So those are all the different probabilities for getting a blue marble. Now specifically, I want the probability that it came from the first urn. So of these two, which one is from the first urn? That's this top one. So that would just be the 1/2 times the 3/7. And then your calculator will do that for you. It actually comes out to be 24 out of 59. Okay. Let's take another look at one of these problems where we can make a tree. It's a medical screening problem. It says most medical tests occasionally produce incorrect results. False positive result. That means a patient tests positive for the disease when they don't have it. A false negative result would be that the patient tests negative for the disease, but they actually do have it. All right. The American Diabetes Association estimates that 9% of the U.S. population has diabetes. So here's the actual first breakdown that we're talking about. We know 9% has diabetes. So let's say 9% are positive for the diagnosis and 91% are negative for the diagnosis. So that's kind of your first choice there. Do you actually have it or do you not? Then they go on to tell us about these false positives and negatives. It says, suppose a medical lab has developed a simple, inexpensive diagnostic test. The test has a false positive rate of 3%. Now remember, false positive actually means that your diagnosis is negative. You actually do not have diabetes. So that's going to fall under this category right here. A false negative actually means you have the disease, actually means you are positive for diabetes. So when I break this down right here, I'm going to break this down into two cases. Positive, I'm going to break that down into false negatives, because false negatives, those people actually do have diabetes, and then those whose test results actually turn out to be positive. Well, false negative rate is 1%, which means those people who have diabetes, 99% of them would test positive using the result. And I'm spelling positive wrong here. Negative, all right, we know negative is associated with false positive, so let's put that category here. False positive, which means they actually do not have the disease, that test rate was 3%, which means that those who take the test and get a negative result, that would have to be represented by 97%. Okay, so again, the false negative, those are people that actually have the disease, so they fall under the positive category. 1% of those test false negative, so the other people who test positively, that's 99% of the people on the test. The false positive rate, that means you're actually negative, so you fall under this category. That's 3% of the testers, so the other 97% of the testers, it comes out accurate and you're actually negative. All right, so that's the tree. Let's see if we can answer the question now. It says, find the probability that a randomly chosen person who tests positive for diabetes. So there's going to be my bottom number. You must test positive. Actually has the disease. So test positive, and then let's put here actually positive. All right, so let's find the test positive. Where is the test positive? All right, testing positive. Right here, I tested positive. So that's 1, right? And here, the test also said positive. We know it's not necessarily true, but the test came out positive. So the test positive is circled there in blue. So that would be, if I convert these percentages to decimals for calculations here, I'd have 0.09 times 0.99, plus I'd have this one, 0.91 times 0.03. Those are all the cases where the test came out positive. Positive, which actually is positive, and false positive, which is negative. On top, I want the ones who are actually positive. So of those two scenarios, I only want the ones who truly have diabetes, which is this case right here. So that would be the 0.09 times the 0.99. If you do that, you get 0.765, which is about 76.5%. All right, so if you think about that, find the probability that a randomly chosen person who tests positive for diabetes actually has the disease. That's not a real accurate number, right? Only 76.5% of the positive test results actually become diabetes. All right, so let's answer this question using the same chart. It says find the probability that a randomly chosen person who tests negative. So we're working just with those who test negative. Those who test negative for diabetes does not have the disease. So let's put actually negative out of those who test negative. All right, so let's first look at all those who test negative. Let's go back up to our chart. Where's the ones who test negative? This is a test negative, right? And this was also a test negative. We know it's not accurate, but the test said it was negative. So that would be 0.09 times 0.01 plus this scenario, which is 0.91 times 0.97. Those are considering all the cases where we test negative, the actual negative and the false negatives. Now we want just the ones that are actually negative. So of those two red groups, which ones are actually negative? That's this category down here. That's the 0.91 times the 0.97. If you make that calculation, you get 0.999. So a 99.9% chance that if you test negative, you actually don't have the disease, right? But a 76.5% chance that if you test positive, you actually have the disease. Okay, so it's far more accurate if it tests negative. All right, that's it for lesson 10.